right. So, okay, so this one is the high pass filter. So let me go ahead and put that one on. Okay, so high pass filter would be that. And let me see. So that is this schematic. Okay, so that's positive 12 right there. Everything, negative 12, negative 12. That's 910 ohms, 0.1, 2 volt input. Okay, so and then when you run it, this would be your schematic. Would be the output of your high pass filter. Okay, so look like okay, so you want to know what is the V out max? Line 60, look like line 962 here. V out max. So you want to do is just put on your cursor. So therefore you click on your cursor and click on this symbol right here. Say cursor max. That will give you the maximum output possible. 2 volt. Okay. And we know that this is going to be 2 volt because this is a unity gain. Okay. So if you put in 2 volt, you're going to get 2 volt output. Okay. So whatever you put in, that's what you're going to get out. So that's your V out maximum. It's going to be 2 volt. Okay. So, and this is cursor, as you can see, verify the value right here, say 2.0002 2 volt. Okay. So that's how you calculate the V out max. Okay. And then to find out the V out at cutoff, you take that, multiply 0.707. Okay. So you want to do is take in, let me see. So you're going to take the 2 volt. So V out at cutoff would equal to 2 volt times 0.707, okay, which is equal to 1.414 volt peak to volt peak. Okay, so therefore we look at exactly where's the frequency at the cutoff. Okay, so that's the next one right here. So cutoff at frequency. So therefore we're going to be looking at that cutoff. So cutoff is going to be so FC would equal to, we'll look at exactly at this point right here. So we're looking at 1.4. So now we come back to this here, look at the cursor. Okay, so 1.4 right there is pretty close. Keep on going down a little bit, 1.14 right there. Okay, so right there is the closest. So the frequency is telling you is 1.753 kilohertz. Okay, 1.753 kilohertz. All right. So let me see back into the Excel. Okay, the Excel, so that's cut off. Okay, now they look at when it's dropping 10 dB, when you're going down by 10. Okay, so you look at that. So you can look at that. It's going to be there. So you look at this one divided by 10. So let me see, that would be at the critical. So FC divided by 10 would equal to this divided by 10. So we're going to be taking this one here. Okay, so 1.753 kilohertz divided by 10 would equal to 0.1753 kilohertz, or same thing as 175.3 hertz. Okay, so therefore now we come back into our output here, and we go down to find the point where it is going to be. So delete that one first. Now put back on. Okay, scroll down until you get to 1.74. 1.75 hertz. So 175, we're almost there. Almost there. Okay, so 175.3. So 175, 176. That's pretty close enough. So 175, 176, you just have to just choose one. Okay, so let's see if I can expand this one a little bit more. Okay, so at that point, V out would be equal to V out at FC over 10 is equal to equal to 200 millivolt equal to 200 millivolt. That's pretty much it. Okay, so that there. Okay, and then you have to convert to VRMS. So therefore VRMS would be equal to, so we have to do is just divide this by that's converted to volt, so that's 0.2 millivolt RMS. Okay, and so that's pretty much it. And you should be able to do that and do your calculation. So your number should be similar to this here. Okay, so do you have any question or comment? Okay, so let me see if it in the chat. See, let me see. Go ahead and exit the screen. Maybe I can see the chat. Okay, let me see. All right. Okay, so Grace, did you understand what I just went over? Thumbs up, thumbs down. Grace?
Yep. I have a question, Sam.
Okay. Yeah, that was for Tech 1, assignment 26, P-Spice, one pole high pass filters. Okay.
Yeah,
Go ahead,
my question is associated to the same circuit. Just curious, by the way. Okay. It's possible to feed a signal to simulate the output of that circuit?
Oh, the circuit that I was sharing with you a minute ago?
In a similar way that we are doing with the logical gates, but instead of feed square pulse, feed a kind of a sinusoid with different components of frequency and see what is the response of the circuit that you just built.
Yeah, you use so when you run it, you put on your information in. So this is your V out. Okay. So that is your V out. Okay, depending on what frequency, that's depending. It's all depending on what frequency you look at. If you look at the frequency, like here, if we're looking at one kilohertz. So if I move my cursor until I hit 1 kilohertz, so keep on moving. So 1 kilohertz, this is my output right here. It's 0.9953 volt VRMS. Okay. All right, so therefore, if I look at the 3 hertz, would be, let me see, 3 hertz would be somewhere up here until I scroll up. 3 hertz is getting close to the maximum. So 3 hertz is here, 3 kilohertz, I mean. So 3 kilohertz, it would be there, and then the output is about 1.7297. Okay.
Yeah, I understand that, but my question was, let's pretend that we are going to generate a kind of synthetic signal with different components of frequency, even some noise, let's say white noise plus some frequency, and we're going to feed that on the input of this circuit, and to see how the circuit responds to that signal. Is possible to do that? using the global function, feed a synthetic signal and see what is the response of the circuit?
What time cycle would you like me to simulate it for?
Let's say we are going to feed a signal that is composed of white noise plus some specific frequencies. Let's say a couple of sinusoids, 50 hertz or 60 hertz here in United States, plus 5 hertz. We're going to create a synthetic signal composed of these 3 frequencies, and we're going to feed that signal, let's say 2 or 3 seconds in total, into
Okay, what you're talking about is radio frequency, and we're not going to deal with this one here in this right now. This is only, we're covering just technician 1. We're covering just the basic. If you want to go into, you look at the signal, mixing 2 signals together, that until you get into radio frequency. And that one, Mr. Pham will cover that.
Okay, thank you.
Okay. All right, so anybody have any other question?
Okay, if not, I start now.
Okay, you're in charge. All right.
Okay, so make sure you understand no class on Wednesday. That's a holiday. Okay, so today we will start with the JFET amplifier. So this one, I think last time we already given to you in the handout for JFET. That means how to handle for the MOSFET JFET. Okay, a MOSFET device are subject to damage from electrostatic discharge ESD. Most devices should be shipped and stored in a conductive form on instrument and a metal branch in assembly or test should be connected to the outground. The assemblers or handler wrist should be connected to outground with a leg of wide and high value of series resistor. Never remove and MOSFET device from the circuit while the power is on. Do not apply signal while the DC power is off. When you have tiring, company first thing they sending to you how to handle. Okay, so today we're talking about JFET amplifier. JFET commonly used to amplify small AC signal. One reason for using a JFET instead of a bipolar transistor is that very high input impedance can be obtained. A big disadvantage, however, is that the voltage gain obtainable with the JFET is much smaller. Okay, so that will be telling you if you want the more gain, then you can using the bipolar transistor. JFET not given to you much gain, okay? And the JFET commonly amplified configuration. It follows common source, common gate, and a common drain. Same thing in the bipolar. You get common collector, common emitter, okay, and common base, okay. That one will be repeated for you when you want to converting a DC circuitry to the AC circuit. So first thing you have to set on the DC source to 0 and replace them by a short circuit equivalent. Second, replace on capacitor by a short circuit equivalent. So that's why in AC circuitry, you never see any capacitor. They will be shorted. Okay? Remove all elements by part by the short circuit equivalent as introduced by step 1 and step 2. Redraw the network in a more convenient and logical form. Okay, so the first one will be common source amplifier. Okay, for common source amplifier, but the first question is what the bias they're using for this common source. That means we're talking about DC bias. What bias? You already know we get a fixed bias, you get a cell bias, and you get a voltage divider bias. So which one will be using for this configuration?
Self-bias?
Self-bias.
Perfect.
Yeah.
Cell bias. And now that we will bring it up to you. One thing. Last time we already explained to you. This resistor here, okay? You don't need it. However, they must be there. Why? The thing is where you apply sideways from the generator here, okay? If you're not using resistor here, they will be shorted to the ground. So you cannot get this sideways, go to the gate, okay? So for this circuitry here, common source input will apply to the gate, and the output will be coming from the drain.
And Mr. Pham, I know you're doing the AC version, but on the DC side, that big resistor like that makes the VG small. Is that correct?
No, nothing. That only makes sure the gate cannot be short to the ground. If you don't have a that 1 mega ohm, so they short to the ground, so that telling you the sideway cannot go to the gate.
Okay, but I was saying for VG, just going back on the DC side just for 1 second, that would be 0. Is that correct?
All right.
Okay, thank you,
Yeah.
thank you.
Okay. Now, let's see what else. Normally, how can we solving the cell bias using what for bias?
You need the transconductance curve.
Now, I asking you you get a fixed bias, cell bias, wanted divider bias. If you try to calculate the current ID, for example,
Oh, you mean graphical?
right, that's what I asking you. You have to using fixed bias, okay, but cell bias and wanted divider bias, you must be using,
The graph.
okay? However, in this case, they not given a graphical. And what else they given to you? Looking into the circuit.
Why can't I do this anymore? Hold on, wait.
You're looking into your circuitry here without the graphical. How can we do?
Well, because they gave you VS, you can figure out IS, and therefore you have the value of ID.
Perfect. Yeah, that means you understand. The thing is, without the graphic, they must be given to you something else. Either they given you VS or they given you the current ID. Okay? So now they given to you the current VS, cubic, voltage VS equal
1 volt.
1 volt. Okay? So now, before we want to do anything, what I want you to do is try to doing number A, B, C, D, E. Do it for me now to see how many people can get through it. That's a DC bias. Nothing to do with amplifier for now. You get any answer, let me know.
A is 5 milliamps.
Okay.
B is 7.5 volts.
Okay, now you said ID, right?
Yes.
IDQ. VS. Okay. That will be 1 volt. 0.2. Okay. That's what you get 5 milliamp.
Yes, sir.
Correct. And VD, right?
7.5 volts.
VD equal VDD minus ID times RD. Okay. Is it 7.5?
Yes, sir.
Okay. VGS
-1 volt.
negative 1 volt. You're perfect. Okay. VG minus VF and VG equal 0.
Yes, sir.
Perfect. Now GM0 will be 2 times ID at divide absolute value.
Is it 7 point? Oh, excuse me. Five.
Who get that answer?
Should be 5.
Let's see. What the ID at that?
10 milliamps.
10 milliamp. Okay. So basically 2 times 10 divide VGS of equal.
-4, but if you want the absolute value, 4
Yeah.
volt.
That's 4. And at. Okay. And GM. The formula equal what? GM, the formula will be equal GM 0.
Hey, Mr. Pham, we can see that on the screen. It's to our bottom right.
On the bottom right.
Yeah, we already got it on the screen there. Where it says GM equal GMO, big parentheses, 1 minus
Yeah,
VGS over VGS off.
I gave it to you.
Yeah. Mhm.
Okay. Basically M0 times 1 minus VGS off. So who got that answer?
3.75.
3.75. Millisiemens. Okay, any question regarding to the DC bias? Okay, if you have a no question, I asking you that before. Okay, we go to the AC. Okay, what's R equivalent?
R1 times R2 divided by R1 plus R2.
Right. If we do calculation, so they will be 10 times 1,000. Equal what?
Need a calculator.
9.9.
Yep, 9.9. That's correct.
Right, 9.9.
It's less than 10. It's correct.
It always has to be less than the lowest individual.
Yeah, that's correct.
Okay, now that telling you what? Okay, they bring it up to you one thing. If you get that one small resistor parallel with a bigger resistor, so basically they ignore that one. Okay? Anyway, they will be go close to the small one. That is the thing. I make sure you understand that. Okay, now going back to that circuitry here. Got the name on this capacitor here.
AC coupling.
DC blocking.
DC blocking
Blocking.
or AC
Coupling.
coupling. That means they allow the AC to pass, but they will be blocking AC, DC, okay? And what is the resistor, capacitor name for that guy?
Same thing.
Same thing. The thing is at the drain, you get both DC and AC voltage. However, go to the load, okay? Go to the load here. That means the speaker. You don't want any more DC. So that's why they need that capacitor to block the DC, okay? And the resistor, the capacitor here,
Bypass.
very good, bypass. They're the same like in the bipolar, okay? Only thing I recommend, when you see the circuitry, only thing you must be know that is a common source, JFET amplifier. Input will be, input and output will be opposite, okay? Or our phase. That's why they showing right here. That's the input and this is the output, okay? That's the only thing you need. Now, the AC equivalent circuit is so. That's for AC equivalent, Okay, and this is on the gate side on this one. You get the input and you get the 1 mega ohm. On the output side, basically you can get just one current flowing from the drain to the source, and the value will be Gm times VGS. Okay, and then if you calculate the input resistance, that means from the source you're looking here, okay, into the amplifier, then you get this one here. Input resistance will be, in this case, 1 mega ohm. Okay, output resistance, if you're looking on the circuitry here, that will be short to ground. Okay, and this also the ground. So that telling you the output impedance, they will be RD parallel with RL. Almost like same thing, okay, on the bipolar. Okay, so in general, any question regarding into that amplifier?
Yeah, I have a question.
Yeah,
How RD is parallel to RL?
RD parallel with RL, right?
Mm-hmm.
Okay, now, if you change it into the DAC, then I know this must be ground, right? Is it okay?
Yes,
Yes.
that's right. That's
Okay.
ground.
And
Mhm.
then also on the drain right here, you go here, you get this one also connect to the ground. So this one and this one in parallel.
The capacitor gets shorted out.
Right, no capacitor in the AC. That's what we're talking about at the beginning.
Mm-hmm. Got it.
Okay,
Thank you.
yeah,
Thank you.
welcome. So in here, they say AC equivalent. That means instead they draw the JFET, you didn't see any JFET anymore. On the input side, then you get a 1 mega ohm. This occurs because the practical zero gate current, the gate source resistance designate are GS approximately equal infinity. So they just put a big resistance here to guarantee if you get a sine wave from an input, they can go to the gate. Now, this is the one they draw. Okay? First thing, the dark side here, that is JFET. Okay? They not draw like we saw this way. No. This is the AC module. So, small d right here. That will be the internal resistance of the JFET from the drain to the source. Okay? And normally they vary big value. So that's why in any calculation, they don't want that. Okay? So we ignore that. Now, for G in, you get this one. For G out, that means G out in here, they put almost equal RD. That means they telling you if they don't have any load, okay, that means no load in here, then they will be equal RD, okay. However, if you get a load, then they have to be RD parallel to RL, okay. So in this case, G out equal RD parallel to RL. And if you want to calculate the gain, this is the formula to calculate the gain. Okay? Minus GM times R load, that means G out. Okay? So basically the formula will be AV minus GM times G out. Okay? They're using R and D in this formula. The thing is they're supposed to have no load. Okay? So the minus sign will be telling you input, output will be inverted. If you calculate for the DC, then you're using the minus sign. If you calculate for the AC, then no minus sign. Okay? They just telling you input, output, out phase. Okay? So what I want you to do, go ahead and finish the part here. Voltage gain. Okay? Input impedance, we already know. Output impedance. Okay, and the V out. Let's see, we get V in 0.2 from peak to peak.
Mr. Pham, can you go back to that circuit real quick?
Yeah.
Thank you.
Mr. Fan,
Yeah.
for F, you got voltage gain equal to minus 1.875. But then earlier on, when we calculate the GM, we got it as 3.75.
Okay. So that in my get it wrong.
So the formula is wrong here, right?
Right. The
Okay.
formula is not wrong.
Oh,
The value is wrong.
oh, okay. Okay.
The thing is, AV will be minus 3.75, right?
3.75, right?
Yeah, time RL, that means G out.
Okay.
Remember, sometimes they're using RL, okay? Let's see, AV minus GM time. They can using G out, or they can be using RL. Small r for AC load, okay? That AC load. Okay, so what the voltage gain you get?
Is it 37.5?
I don't know, just tell me GL you get.
I haven't got CL yet.
Yeah, the thing that you need that in order you can calculate the AV. G out will be equal 1.5K parallel 10K.
$2.875.
2.875K.
Oh no. Wait, that might be wrong.
Okay, tell me what you get. So I don't have to calculate it.
$4.89.
4.89K.
I get 1.304.
Oh, man.
Okay.
Oh,
This
man.
isn't an
Right.
Yeah, I get
Oh,
1.30.
I stand corrected.
Which one correct?
I was going in the wrong direction.
1.3.
So what answer right?
1.304.
1.3.
Should be close to 1.5.
1.5 or 1.3?
1.3.
50-50.
1.3, but it's close to 1.5.
How come they can be close to? Okay,
He talks faster.
I using my calculator.
I got 1,304.
Yeah,
Yeah.
1.3, yes.
Yep.
If you take 1.3 and 1.4, you can get the median be 1.4, and then that'll be 50-50.
That's okay.
I'm just saying it should be close to 1.5 because it's a smaller number.
That's okay. No big deal. If that calculation you cannot get through it, what can you do? Okay, then AV will be equal minus GM times G out.
Is it negative 4.89?
You say negative 4.89.
Yes, sir.
Make sure the guy can try to get the same answer, okay?
So my last answer was 4.875 before everyone said it was 1.3.
That's okay.
But which one is it?
You take 1.3 times what? 3.75.
Correct. Right. Okay. So, all right. So I was right. Sort of. Close enough.
4.9. That'd be fine. Okay, what we are? Okay, V out. V in times the gain. Okay, V in 0.2, I believe so. Times 4.89. For the AC, we're not using the negative, okay?
0.978.
Yeah, 0.9, 0.98, that'd be fine.
Stefan.
Yeah.
Now the input is 0.2 volt peak to peak.
Okay, then that will be peak to peak.
So 0.98 volt peak to peak then, right?
Yeah.
Okay, thank you.
Okay, any question regarding into the common source amplifier? Okay, if it's not, okay, let's see. That we done. That one they're just talking about the phase relation. Common source amplifier configuration at 180 degrees of phase. Okay, of phase shift between the input and output. Now, what I want you to do, you're doing this thing for me. Okay, do that calculation for me. We already done almost everything. If you get any answer, let me know. And if you can do without looking into any note, that'd be perfect.
Is A negative 2 volts?
Okay, so VGS minus 2 volt. Okay, VGS VG VF VG equal minus 2 VF equal 0. And if you want to calculate the current ID, make sure you know the formula. IDSS 1 minus VGS VGS of square. And make sure you get the VGS of minus 8 volt. Who get the ID?
$5.6 milliamps.
So you can see ID equal 10, 1, minus 2, divide minus 8 squared.
I think I'm doing the math wrong because I keep getting a value higher than IDSS.
I'm doing it wrong because I got negative 10 milli. Oh, I know what I forgot to do.
5.6.
I already gave it to guy the equation.
Yeah, it's like 5.625.
Make sure that cannot be higher than 10.
Okay, did we say it was 5.625? Is that correct?
Yeah.
Okay, I got it now. I don't know what I was doing there. I was doing something wrong with the equation.
You see the I given to you ID equal 10. Times 1 minus 2 over minus 8 square. Okay, let's see. I do calculation. Minus 2 over minus 8. So 2 divided 2 8. 0.25.
At first, I was using -8 as the value of VP, so I thought we were saying VGS off was +8. So that was throwing everything off for me, I think.
Okay. So 1 minus 0.75 equal 0.25 times 10. Is it 2.5?
Yes, sir. 6.625. Have 5 guys. I can't even have 5.625.
Okay, let's see. I try again. Okay. 1 minus 0.1 minus 0.25 equal and square. Okay, 0.56. You're right. Answer will be 0. Okay, 56.
Times 10.
Okay. Milliamp.
Should be times 10.
Times 10.
Oh, times 10. Okay. Let's see. Oh, square times 10. See, man. 5.625. Okay. VD.
8.75 volts.
Same.
Point 7.
Same.
That's okay. 75 volt.
VD, I get 11.25 volt.
Which one?
VD,
VD? You get it wrong. Another one. Okay. I try to say VD.
you got a VDD minus ID times the resistor.
ID times RD. Okay. VDD 20.
Oh yeah, I got it wrong.
Okay.
I forgot to minus it. 10.54.
GM0 will be 2 times 10 divided by 8,
2.5 milli.
20. 20 divided 8,
Yeah, it's negative. I got negative 2.5.
2.5. They cannot negative.
No,
Oh
no
yeah,
negative.
you're right. Sorry, sir. Yes,
Absolute of 8.
2.5.
And what GM you get?
Minus 3.75.
How come you get a minus? They
No,
can-
no, no, sorry, 1.875.
Oh.
Sorry, I was looking something else.
Okay, so make sure you get that the right answer up to number E. Make sure next time I give it to you, you can do it without looking into any formula, and you'll be okay. Okay, now if you already done up to GM, I want to know what GL equals.
Is it equal to RD?
Now we calculate AB later, but we want to calculate GL. Output impedance.
I was going to ask the same thing. Is it 2K? Is it just the value of? It's not the value of RD now that we lost RL.
Since there's no load, so it should be equal to RD, right?
Perfect.
Yeah, okay, thank you.
Yeah.
The thing is they have a no load. And now you can calculate the AV minus GM times output impedance.
Minus 3.75.
You say minus,
I have the same.
3.75.
let's see. Can you tell me again?
It's minus 1.875 times 2 K.
Yeah, what the answer?
Minus 3.75.
Okay, minus 3.75.
And you said we dropped the minus, right?
Now, if you calculate the gain only, then you can put a minus sign. However, when you calculate the V out, you're not using the negative for AC. The thing is, normally when you get the interview technician job, they just asking you not go into that kind of detail. Why? The thing
Mr.
is, the
Fam,
people, supervisor in the company, they've been working for a long time. That means maybe 10 years ago. And that time, not much people understand the JFET. They can understand bipolar, but not the JFET.
hey, Mr. Pham, I'm trying to understand this now. Minus GM times Z out gives you negative 3.75. Is that correct?
Correct.
So I thought that that would be the gain, and for the gain, you don't have a sign.
No, you get a sign just telling you they will be inverted.
Oh, okay. $180 out of phase, right?
Right. Opposite.
Okay. But when you have the regular V out over V in, then that would be no sign, correct?
Right, I think AC. You cannot put a minus sideways. No,
Okay,
not be minus, we pick to pick.
okay.
Now, Mr. Fan, on question number 8, you got output impedance Z out equal to small RL. What it?
No. Normally for the output impedance, okay, they can using to output impedance. Some textbook they using the out. Some different they using R small L.
Okay, it's the same thing then. Basically, different both use different notation.
Right.
Okay. All right. Thank you.
The thing I using sometimes ZL or R small L. So if you guys get the reading a textbook, you can understand what they're talking about. So they can build the amplifier either using cell bias or fixed bias or voltage divider bias. It doesn't matter. Okay, and the question on the common source amplifier. Make sure if you're confusing anything or do not quite understand, just let me know. The thing is we're not going back this anymore, only working on the problem, but not try to explain in detail. Okay, now let's see. Did the same thing. Now we go to a next one. That will be common drain. And they get another name, source follower. Same thing in a bipolar, okay? You get a common collector or emitter follower. Okay, on the JFET, they're using the source follower. And now if you're looking into the circuitry, and you can recognize that using the cell bias. Okay. Input will be connected into the gate. However, output will be taken out from the source.
Okay, Mr. Pham, this one here, this one is graphical.
Exactly, but normally we're not using graphical. Okay,
All right.
we're not going to the detail to calculation. So that's why we're not giving you any more detail. However, I just give a full picture. When you're looking into that, you know that will be common trait. Input go to the gate, output from the source. Also to get a name as a source follower. So you already know C1, that's the DC blocking or AC coupling. C2, same thing. Okay. And also they're telling you input impedance. Okay. And where is the output impedance? Z out or Z in. Now this is the AC circuitry. Okay. AC circuitry, then you can see in the V in, that means the gate right here. That is the gate. Okay. And now they draw opposite. The drain will be drowned, common drain. Okay. And also you still get the EM times VGS current flowing. And this is internal resistance. Ignore that thing. Okay. And you can see what is the output impedance right here. Now, try to go into something else. The circuit below show a common drain amplifier. Usually refer to add a source follower. If they say source follower amplifier, then you must be understand that is the drain amplifier. Okay. On this one also they agree using the cell bias. So that's why they must use something here. Vs equal 2 volt. Okay. And also you can get the load resistance equal 1.8 K. Input output will be in phase. Now, for that circuitry, we want you to do for me. Calculate, okay, A, B, C, D. Okay, try to see how many students can get through easier for me.
Is A 8.3 milliamps?
Yeah, just let the other people, they can try to see they get the same. That are very simple. Okay, so the one already calculated. I can give you that ID equal answer will be 8.33. Okay. And I believe you guys can calculate the VGS, right?
It's -2.
Yes. Okay, and I know what VD you get and what GM 0. GM. Okay. Input impedance. Output impedance. And the gate.
VD equals VDD, so it's 10 volts.
Okay.
GM0 is 3.75.
You get 0 what? What GM you get?
Oh no, I'm sorry, I got 3.75.
Okay. 3.75. I'm not doing a calculation.
Yeah, someone stop me if I'm off.
Make sure the other people can get the same. Otherwise, you guys can get a big problem.
The next one's 2.8125.
Just a minute.
I agree with that.
Let's see. Okay, you said GM equal what value?
Catherine?
Sorry, 2.8125.
You say, can you repeat for me?
Oh, yes, 2.8125.
8, 1, 2, 5.
Z
8,
in is
not
just 1
7.
mega ohm.
2.8, not 7.
J in will be
1 mega ohm.
is it 1 mega ohm, right? G out
1.8K?
out. I give it to you G out. If you're looking at formula, G out will be R here,
RD.
parallel
Oh,
Okay. Thank you.
1 over GM. Depending on what type of the amplifier, common short or common drain, that's a different for GL. And the formula I already gave it to you. Let's see, what RF equal 240.
Is it 85.182?
Okay, let's see here. We can be some wrong in here. Okay, GL will be RF. Okay,
Never mind, never mind.
no, okay. Let's see, RF. Okay, so
Scroll up just a little bit more. No, the other way,
No,
the other way.
I want to see something here.
Oh, okay.
I see something here. For this circuitry, you get RF 240. Okay, and also you get a load 1.8. Okay, so basically, GL is not RF parallel with 1 over GM. GL will be this one here. RF parallel with 1 over parallel with a load. That is the right formula. Some the textbook sometimes give a confusing. Also, I can give you this formula for AV. AV will be GM times G0 divide 1 plus GM times G0. That is the formula correction. Okay.
Mr. Pham, on AIDQ, you get 8.33 milliamp. How do we get that one?
What number?
A. IDQ,
IDQ.
the current on the drain.
IDQ, basically, let's see, you take the VF
VS
divide IS 2 volt, right?
uh-huh.
IS will be 0.24.
Okay.
Okay, 2 divide 0.24. That one you get 8.33.
Okay.
Did anyone else get Z out?
What the hell you get?
Mine has to be wrong because I get 0.3544 and some change.
Yeah, I get 0.531
Huh.
and some change.
And
I'll go back to the drawing board.
I'll take the change.
Put it in the change jar. So for Z out, we're doing 1 over RS plus 1 over RL plus 1 over GM.
Yeah.
Okay.
3 parallel.
Okay.
Remember, I get IS parallel 1 over GM parallel with RL. So basically, they will be equal 1 over 1 over RL. 1 over 1 over GM plus 1 over RL.
I got 132.6.
I don't know what the value you get. Okay, but that will be 1 over 1. Okay, and 1 divide to 1 That means plus GM, right? And the formula for AV. Okay, will be equal GM times G out divide 1 plus GM times G out.
Mr. Pham, I got a question for you.
Yeah.
Where you was doing that one, you was just doing right before your last one, 1 over RS plus, and it says 1 over, and then it says 1 over GM. When you take the reciprocal of that, wouldn't that still be, because you got 1 over GM, which would just change.
Yeah.
Which
So
would,
it's a reciprocal of a reciprocal, which is the original number then, right?
yeah, which would be 1 over GM.
No. They
Wouldn't it?
parallel with 1 over GM.
I know, but what I'm saying is,
That's why when they parallel with 1 over GM, so it's supposed to be 1 over GM.
But doesn't that just give you GM?
Right.
Right.
oh, okay.
So that just means take the regular value of GM.
Right.
When you take the value of GM, since it's a millisiemens, do you have to change that to siemens?
Yeah, milli.
Or you keep it as milli?
You change it.
Depending on IS you want to be ohm. IL you want to be ohm. Okay. Then GM you must be changed to Siemens.
Oh, that's why I'm not getting it.
If you're using the kilo ohm, then GM will be okay. Okay, so make sure tomorrow take 2 will be on Tuesday. Take 1 will be go with Mr. Tai. The thing is we don't have a meeting on Wednesday.
But there's a meeting on Thursday, correct?
Yeah, still get a meeting on Thursday. The reason is they take 2, they get only 1 day on Wednesday. So that's why Wednesday is a holiday. So I have to take 2 on Tuesday, tomorrow.
Okay.
So we will be going back with the amplifier, okay, for next week. And also we can get one more for MOSFET, okay. Then we're done with the major electronic. Still get few things, but it's not a major, like integrator, differentiator, comparator, okay. That will be done quickly. Nothing calculation, nothing a big thing. Someone get 0.27 for gain. I don't know right or wrong.
50-50.
I just got 132.7 for Z out, so now I'll work on that now.
But the thing is, 0.27, I don't think that can be a right one. The gain should be less than 1,
That is less than 1.
but it's not too low.
Oh, you think that's too low, Mr. Pham?
Exactly. But, you know, next week, we return with the thing.
Then the answer could be 50-50, huh?
Yeah.
Yeah, I went to a couple of calculations. Still comes up the same number.
Yeah, I agree with Sam. I got 0.271844191.
Okay.
And that was nano, right?
No.
What was the NS then?
It's the gain.
No. I was asking Sam, what was the NS on the end of his number?
NA
there's no
means
NS.
no answer. There's no
Oh.
unit for it.
Yeah, no, in it. Okay, so go ahead and working on that. Next time we return to this thing.
Sounds good.
Okay.
Thank you, Mr. Pham.
Any question? Okay, if it's not, then we'll see you guys next week.
See you tomorrow, Mr. Pham.
Yeah,
All right. Thank you, Mr. Pham.
okay.
Thank you.
Yes, sir.
Okay, you know, take you next tomorrow.
Okay. Thank you.
You are welcome.